Good evening. How are you guys doing? Hi, I'm good. I'm doing okay. Not bad. I'm thinking about one question I got wrong in the last class. I was trying to do it now, but I still got it wrong. I wonder what's wrong. Okay, so we did determinant for 2 by 2, 3 by 3, and we talked a little bit about 4 by 4 in our last class. Today,
like doing it, reduce it to a 3 by 3 and then a 2 by 2.
Or you can use other methods. So this section is short, not long. My goal is to finish this section and then go to chapter 3. Or at least watch a video for chapter 3 so that we can have our materials ready for our next class. Quiz? No, I said materials ready for the next class. So in the next class, I don't have to explain the background information or everything. We can just do examples. So 2.2 talks about properties of determinants. We know what determinants is. Determinants are very important because that tells us whether we have an inverse or not. We'd like to have inverse, so if you don't have an inverse, then you have to use different method to solve instead of using the inverse method. Now, there are a few properties we have for determinants. 2 of them we already know from before. One is if you have the entire row or entire column full with zeros, then determinant is 0. No explanation is needed, no work is needed. You can simply say rows full of 0 or column full of 0 is determinant 0. Another one you learned from before is that if you have 2 same rows or say 2 same columns, then determinant is automatically 0. Now the new 3 information is that determinant of the transpose matrix is same as determinant of the original matrix. And then we have multiplication. If you multiply a matrix either on the left or on the right, it doesn't matter, by an elementary matrix, then the determinant of the product is the product of the individual determinant. So determinant of EA is same as determinant of E times determinant of A, which is same as determinant of AE. So AE and EA, they are same because E is an elementary matrix. But this is not true if you don't have an elementary matrix. If you multiply any 2 random matrices, then the product of AB is not same as product of BA. However, we have the same rule. Determinant of AB is same as determinant of A times determinant of B. Okay? So we have the multiplication rule. Determinant of the product is product of the determinant. The first question is asking, well, is this true for addition and subtraction? Is the determinant of the sum of 2 matrices or difference of 2 matrices is same as the sum of the determinants or difference of the determinants? Is this true or is it not true? What do you think? What is this? What do you think? Any idea from anyone?
I think it's correct.
You think it's correct? If it's correct, then you have to prove it. If it's wrong, then you just have to give a counterexample. So it could be correct, or it could be not correct. If it's not correct, then all you have to do is find out a counterexample that is false. So let's work with a 2 by 2 matrix. Let's say A is.
If it was going to be correct, then we would list it in theorems.
Yes. Good observation. Good thinking. Good logic. So give me a 2 by 2 matrix, any 2 by 2 matrix. What elements you want to have in a 2 by 2 matrix? You can have anything.
Zeros.
All zeros is not possible because determinants of a zero matrix is 0, and we don't want to have a 0. 1, 2, 3, 4. So what's the determinant of 1, 2, 3, 4? Do you remember how to find determinant? 4 minus 6. So right minus left. Our right diagonal is 1 times 4, 4. And you're subtracting 3 times 2, 6. That gives us -2. Now let's see another matrix B. Another 2 by 2 matrix. Two, 4, 6, 8. So what's the determinants of that? 16 minus 24, which is -8. So if this is true, that means if we add A plus B and take its determinants, it should be -2 plus -8, which is -10. Okay? If this is true. Now let's see if we add A plus B, what do you get? 3, 6, 9, 12. Do you guys remember how to add matrices? Okay. You add each element on their positions. So determinant of A plus B, what do you have? 3 times 12, 36 minus 54.
How do you get 4 and 6 for a determinant of A? 4 minus 6. How do you come up with that?
See, okay.
Yeah. Oh, okay.
1 times 4 is 4, and you're subtracting 3 times 2, 6.
I get it.
So is 36 minus 54 gives us 10? -10? -18. So are the same? Nope. So is this true? No. So I'm going to ask you this type of question in the exam. Is this true?
I thought we're not doing proofs.
This is not proof. This is a counterexample.
This is no proof.
It's a counterexample.
You don't want to.
I'll ask you the multiplication. Is this true? Or the addition or subtraction. Is this true? If it's not true, then give me a counterexample. But I'm not going to ask you if this is true, then prove it. No, we actually don't prove by counterexample. The counterexample disprove the statement.
Chapter 3 have to go?
We're not going to do any proof in this class. No proof. But we're going to do this one. Prove this one. It's a fun proof. It says determinant of the inverse is reciprocal of the original determinant. Determinant of the original matrix. Prove that determinant of the inverse matrix is inverse of the, not inverse, what did I use? Reciprocal. Reciprocal of the determinant of the original matrix.
Yeah.
It's a fun proof. Any idea how do you start?
But like, I can't prove it by just picking one example. That's not.
No, we never prove by example. We disprove by example.
So how do I prove?
Let me give you a hint. We all know the proof. We all know if you multiply a matrix with its inverse, what's the result?
1, -1.
You're talking about matrix. If you multiply a matrix with its inverse, the product is identity matrix. So start from here. What do you think?
Ashford mean in the bottom?
What is the period?
Oh, sorry.
It's a period. I gave you the first line. Any idea? What comes next? No idea? Do you want me to give you the
So
second hint?
If you isolated A inverse and then took the determinant of both sides, you would not be something. I don't know.
Before you isolate, let's find the determinants. What type of matrix is identity matrix? Definitely square. Okay, it has another name. What's the name of the identity matrix? I mean, type. What type of matrix?
No, reducer. Not rectangular.
It's a triangular, but special type of triangular.
Yeah.
What's the name of that special types of triangular? Start with D. Ends with L. Diagonal. Identity matrix is a diagonal matrix. What's the determinant of a diagonal matrix?
The product of all of them back.
Good job. So if we have I2, 1001, what's the determinant of this I2? 1. So determinant of any triangular or any diagonal matrix is the product of their diagonal elements. Here, our diagonal elements are 1. So 1 times 1 is 1. So we know this is 1. What can you do with the left side?
You can take A times negative or the inverse A, and you can change that into I, and then it's
But you're proving determinant of A inverse is 1 over the determinant of A.
yeah, well, it's not.
It is.
What? How do you? No, it's A times inverse of A is I, and then you're back and you have the same thing on both sides.
So that means we don't have to use that. I mean, we shouldn't use that approach. Why do they apply the determinants? What's the determinant of the product?
Is it the determinant of A times the inverse?
Good. See the property here? Determinant of two matrix. Determinant of the product of the two matrix is product of the individual determinants. That means determinant of A times A inverse is determinant of A times determinant of A inverse. Right? Because this is one of the property. Another answer is in front of you. What is your last step? Good job. Divide by what? Determinant of A. And we are allowed to divide because determinant is a number, not a matrix. So determinant of A inverse is 1 over determinant of A matrix. Exactly. That's why I put it here. I hate proofs, but there are some proofs I love them because they are so cool. Any question? Emmanuel, no phone.
What's the difference between the identity?
You don't have to take notes on your phone. Either take notes on your paper or don't take any notes at all. Put it in, please. Thank you. And also, if you are absent on last class, I actually didn't tell you guys. I almost shouted, I mean, not shouted. I almost yelled at everyone in my first class about the homework. Homework or the review homework, any type of homework. I don't want to see only the numbers, only the answers, okay? The purpose behind the homework is for you to have some practice. If you just give me some answer from copying from internet or use AI to get the solution and just give me the answer, why did I even bother giving you the homework? Okay? If you don't learn anything from the homework, don't even bother doing it. They're going to lose your grade, but at least I don't have to check and see all these things. Please, if you do the homework, show all the steps and try to show them correctly. In this process, if you have some numbers wrong, you will not be punished. This is what it means to grade by completion, not correction. Completion doesn't mean you give me anything you want. My name is this, I do this, I love that, and I complete the homework. No, the homework said do math, so show your steps. Don't tell me about your anything, whatever you want to just write to get the completion points. Completion point doesn't work that way. So I actually checked every one of your exam one by one. I counted how many questions you did and how many you did not. I did waste a lot of my time, and that's why I was really angry when I first met my other class, and I just, yeah, I was angry, especially after grading the review homework. Like the review homework is supposed to be a good practice for the exam. So if you just give me the answer, one is 15, number 2 is 13, number 4 is that, and then the question for the one, if you have A inverse or not, what many of you did is you found A inverse and the determinant and told me all that the A inverse doesn't exist or this and that. You know, instead of that making me happy, that actually got me angry. You know why? Because we didn't go over determinant yet. And you're telling me using determinant, which you did not find, which you did not show in the paper, suddenly you're saying determinant is 0, so inverse doesn't exist. Like, do you want me to be happy for you? You're clearly showing me that you used AI or you used Google or you cheated. Okay? If you don't show anything on the paper, don't mention that. If you do mention something, make sure you show your work. Even though I'm not going to grade the normal in class, the sectional homework, I'm not going to check the numbers, but I do check the steps. If you don't show me steps, I'm not going to give you credit. Okay? I'm not going to give you points. Especially you. No steps are shown. You got me really angry.
What if there is like, there isn't really any step to show, like,
Every math has some steps to show. Math. If you're talking about row echelon form, reduced row echelon form, those questions, then I understand. But other than that, everything has a step to show.
like for the elementary matrix, like I can derive the answer, the only other step I can think of showing is a step where I multiply by the,
So you have to tell me row 3 times that, or swap 2 rows, or that. Like what operation you did. That's the step. What operation you did.
the only step that I can think is the check that I can show, but,
Then at least check that, but which you didn't show.
but,
Mhm.
but then, there is so much I'm rushing and, okay.
Yeah. So I'm telling you guys, if you take your homework, even the in-class homework, not all of you got full points. Gregory, no answers. The work. I want to, not Gregory, sorry, Emmanuel. I want to see all the steps. If I don't see steps, you're not going to get any points. Okay? I'm telling you. There was only one homework I didn't check anything. I just gave points to everyone. I forgot which one. But besides that, I do check how many you did, whether you did them correctly or not. Number could be wrong, but the steps, I'm looking for the steps.
So you already like check homework 6 for everybody?
I did everyone's homework, the previous homework. And you have a homework 1.5, I think, to tonight.
Oh.
And for next Monday, you have another homework, chapter 2.1, 2.2. Yeah, like I do use my time. I wasn't able to manage my time before, but when we had online classes, I tried every single day to grade some people's homework. And that got me angry. Okay, anyway, so 4x4, we discussed a little bit in our last class that Either you can use cofactor expansion, or you can use inspection, or you can use row echelon form to reduce it into triangular matrix, or at least some zeros. So if you do use cofactor expansion, all you have to do is pick one row or one column and then expand the entire matrix about that row or that column. In this example, they chose column 1 and they expand around that column. So they took the first element, and here the sign does matter. The first one is positive, then negative, then positive, then negative.
Always positive and top left.
You start with positive always, and then the sign alternates. So you take the first element. If you take the first element, that means you're not using first row or first column. So you're left to it the 3 by 3. So you take the determinant of the 3 by 3.
And now the 3 by 3 is top left, the negative?
No, positive.
Again.
Every new matrix starts with positive. And then you go to the next element. The next element is negative. So negative of that number. So you're not going to use this row or this column. So you're left to it first row and the last 2 row. You take the determinant of that. And then you go, let me change the color to purple. We have the third element. So you don't use the third row or the first column. So you have first 2 rows and the last row. So you take the determinant of those. And lastly, you have the last element, which is a minus. So minus the 4th element times, if you don't use that, you're left to this determinant of that. So basically you do same thing depending on how many elements you have on your column or on your row. And for that 3 by 3, you can use the method I told you by copying the 2 column next to that. You can use the right diagonal minus left diagonal, or you can do another inspection if you have more zeros. Now we did this question before in our last class. We have 4 by 4, but we see that we have more zeros on the first column. So we can expand it on the first column. As a result, we're not going to use the first column or the first row. And we have a 3 by 3 matrix here. But in this 3 by 3 matrix, we have more zeros. So we can expand again. We can expand it on the third column. We're not going to use the third row or the third column. So it's 3, but this position is positive. So you start with plus, minus, plus, minus, plus. So plus 3, you're not adding. This is just a sign for that element.
So then you take the determinant of the 2 by 2.
Determinant of the 2 by 2, and you got that 3. So all of these, they're multiplying. When you multiply them, the final result is a determinant of the original one. So inspection method is easier when you have more zeros to work with. However, our life will not be so easy all the time. For example, if we have something like this, it looks so scary. If you have something scary looking like this, then you have another two choices. Either convert them into a triangular matrix. It could be upper triangular or lower triangular, it doesn't matter. If you have a triangular matrix, then the product of the diagonal, the product of the elements in the diagonal is a determinant.
You change the upper half to 0.
Or lower half.
Elementary row operation.
Row operation. All the row operations. Or you can just have as many zeros as possible and then expand it on the one we did before. Okay, so you have 2 choices if your matrix doesn't have more zeros. If you cannot use the inspection method, make it into something so that you can either use the inspection method or you can use the diagonal method. And this is what you have to do now. Use one of these methods, or if you don't like any of this method, you can use the cofactor expansion. In my first class, we did cofactor expansion. So I want you to try these 2, because you can watch the cofactor expansion in the last recording. The second one is convert this into something so we can use inspection method. Or convert this into diagonal matrix.
Method, the other method that you thought, the having the two.
Here. One you have more zeros. I mean, this is a cofactor, but it's called an inspection because first you observe what type of matrix you have, and then you use cofactor. So cofactor, the normal cofactor means you're going to do cofactoring 4 times. In inspection method, you have to use cofactoring. Let me erase all this so I can be clearer to you.
These are different.
These are different methods.
They look very. What's the difference?
Oops. The difference is this method is useful for any matrix, any type of matrix, the cofactor.
Yeah.
But the inspection is only when you have more zeros. Inspection means observe if you have zeros or not.
Okay.
Like, can you make it shorter? You're inspecting your matrix, whatever
But
matrix
you're
you have.
just doing cofactor expansion thing. with
Less time.
Making zeros.
Mhm.
It's just.
Or you can use the triangular matrix so that you can have the diagonal as your determinant. So convert this into something like that, while you have zeros, or convert this into triangular matrix. It could be upper triangular or lower triangular. Use any of these, and if you're done, there is one other matrix we have, where you are finding all possible values for C, which will make the matrix singular. And singular means the determinant is 0. So 2 questions to do. Go ahead. And let me pray. Determinant is 0. When the determinant is 0, it becomes singular, means it becomes bad. It becomes single, the bad one.
So what's the difference between the identity and the elementary?
Identity matrix has strict format. I2 means 0, 1, 1, 0. I3 means 1, 0, 0, 0, 1, 0, 0, 0, 1. Identity matrix has only 2 numbers, 1 and 0. The diagonals are 1, everything else are 0. These are identity matrix. Elementary matrix is, it's look like identity matrix. I mean, not look like identity. It's any matrix that you can obtain from the identity matrix by applying only one row operation.
On the identity matrix?
You can get that matrix from one matrix to another matrix by obtaining only one row operation. Could you what?
Could you go back to the cofactor expansion stuff?
Okay, let me. How do I cut? Cut. Okay. So, 2 questions. So elementary matrix are one step away from identity matrix. Like if you apply only one row operation, it will turn into an identity matrix. For example, this is an elementary matrix. 0, 0, 1, 0, 1, 0, 1, 0, 0. Why is an elementary matrix? Because if you swap these two, it will turn into an identity matrix. Right? Or this is another identity matrix. 2, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 1. Why is an elementary matrix? because if you divide that by 2, you'll get the identity matrix. And yeah, how come you're not doing anything? What happened? I give you the structure. Convert it into a triangular matrix.
Am I supposed to like, find out what the
Which one you're talking about, the left or the right? The left or the right, which one you're talking about? Left? The right? For the right, it says, what is the determinant of this matrix? And then in this determinant, it will be an equation with C. So what number you don't want to have for C so that the determinant will not be 0?
1 and 1?
What -1? How do you know -1? Why do you think the -1 will cause a problem? Mhm.
Just, at -1 will become 0.
True, but if you have a -1 here, then you have -1, which is -2.
No, but that one is 1.
So you're saying 1 and -1. Nope. First, you have to find the determinant and figure out. But before that, who is done with the left page? Almost. Triangular matrix. Which one are you using? Oh, man. In my earlier class, they did the COFACTOR expansion. I wanted to try one of these. Oh, but before that, when I was praying, suddenly something clicked in my mind. I should read these directions because something is different here. I just remembered. So if you use the 3-row operation, they're not exactly the 3 operation we used before. First of all, if you interchange 2 rows, then you have to multiply the determinant with a negative sign, which we never did before. So in your row operation, if you swap 2 rows, that means multiply the determinant by -1. And multiplying a row with a non-zero constant. If you multiply any row with a non-zero constant, then at the end, whatever number you get for the determinant, you have to multiply by the reciprocal of the same constant.
That's really only useful when we're doing the triangular.
Triangular or the inspection doesn't matter. If you use the 3-row operation, these are the things you have to be careful. Swapping 2 rows, change the sign. Multiplying by a non-zero constant means you have to multiply by its reciprocal. And the last one, adding or subtracting multiples of 1 to another row, it doesn't do anything. That's why I didn't get the correct answer. So like, people say when you pray, you can remember all the things you don't remember. That is so true. Like that the entire time I was keep thinking about that. Like, why I didn't get the correct answer? And now I know why, because I didn't follow these things, these two rules. So let's use one of these. Which one you want to use? The triangular one or the inspection one?
Use the triangle.
Triangular.
And then I'm gonna continue with this.
Okay, great. So triangular, you can use lower triangular, upper triangular, doesn't matter. Our goal is to have above or below one of them. One of the two sets has to be 0. So let's go with these to be 0. Let's see if we make all of these 0. What do you get? So we are changing row 2, row 3, and row 4. Row 2 plus 2 row 1, perfect. And how about row 3? The current row 3 plus row 1, and the row 4 is current row 4 minus 3 row 1. Adding or subtracting multiples of one row with another row doesn't do anything. Okay. So we just added or subtracted. We didn't use the other two rules. No. Sign affects if you multiply by, if you swap two rows, sign changes. If you multiply just by a number, then you have to divide by the number. So let's see, row 2, negative 2, 4, 0, 4, and you're adding 2 row 1. So 2 times 2, negative 2, 4, 4. And then row 3 is negative 1, 2, negative 3, 1. And we are adding row 1, 1, negative 1, 2, 2. And lastly, the last line, 3, negative 3, 1, 2. And we are doing what? 3 times row 1. Negative 3, 6, 6. And when you subtract, the sign changes. Okay. So 2, 2, 0. 4, 2 gives us 2. Then we have 4, 8. So we are adding here. Then we have 0, 1, negative 1, 3. And then we have 0, 0, negative 5, negative 4. So we do not change anything in the first row. So negative 1, 1, negative 1, 2, 2. Then we have 0, 2, 4, 8, 0, 1, negative 1, 3, 0, 0, negative 5, negative 4. We still don't have our diagonal. So we want, let me change this color to red. We want this to be 0 and this to be 0. We can do inspection, and it will be easier if you get only one more 0. Then it will be even easier. Right? So if you do inspection, first we are going to explain around this. So we have 3 by 3. Then this 3 by 3, this is gone. So we have 2 inspection to do, 2 cofactor to do. So if you make at least one of them 0, this one or that one, we can use inspection. Let's make this one 0, row 3. So new row 3 will be old row 3 and what? Half of row 2? Half of row 2, right? We can get this 0. So, current row 3, 0, 1, negative 1, 3, and half of row 2, 0, and then half of 2 is 1, Half of 4 is 2, half of 8 is 4. And when you subtract, the sign changes. Minus, 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 minus. So you get 0, 0, negative 3, negative 1. So 1, negative 1, 2, 2, 0, 2, 4, 8, 0, 0, negative 3, negative 1, 0, 0, negative 5, negative 4. And then we can do a cube inspection here. Or you can change negative 5 into 0. It's up to you. If you want to change negative 5 into 0, then we need the help of this one. So we have to work with fraction. So instead we use inspection. First, we are going to expand around this. So we're not going to use first row or first column. So determinant 1 times. We have this new matrix. So in this new matrix, we can expand around this number because this is the non-zero. So we're not going to use this or that, right? Are you guys with me? Do you understand what I'm doing? Okay. So 1 from the big matrix, 2 from the small matrix. And once you have 1, 2, then you have this tiny 2 by 2 matrix to use its determinant. So what's the determinant of this tiny matrix? Let me change the color here. It's 2 by 2. So right diagonal minus the left diagonal. So right diagonal is 12. And you're subtracting the left diagonal, 5. Now let's see, what do you have? 1 times 2 times 7, which is 14. Good job, we got it. The answer is 14. Yes. So with my earlier class, we used cofactor. Like we did cofactor 4 times, which is hard. I mean, took time. Not hard, took time. This one took time because we're explaining, doing, and everything. But if you do it on your own, it should be shorter than if you use cofactor expansion. See, it takes time. But the answer is 14. Any question on this method? Is anybody lost? Not lost. Which part? All of it? So you're finding 4 by 4 determinants. For 3 by 3, we have easier method. Rewrite the first 2 column next to the right column, and then you do right determinant minus left. That method is specifically only for 3 by 3. You cannot use that into 4 by 4. That means we need new methods. So one of the new methods is using inspection. So how do you use inspection? You look. It is cofactor, but the difference between cofactor expansion versus inspection is that in inspection, first you inspect your matrix. Do you have any row or any column with more zeros? If you do, then you're going to apply the cofactor, but not 4 times, only 1 time or 2 times. Unfortunately, the matrix we don't have any matrix with more zeros. All of them have 4 numbers, only the third one has 1 0. So inspection method is troublesome here. So what if we turn this matrix that has more zeros instead of more non-zero entries? What if you convert it into something that has more 0 entries?
So you have to get like.
So you are using row echelon form. So when you use row echelon form, either you convert it into a triangular matrix or have at least 5 zeros and you are done. So even though my initial goal was to have a triangular matrix, but when you have 5 zeros, I start because we don't have to find another zero.
And then once you have 5 zeros, what do you do after that?
So one row or one column has 3 zeros, and another row and another column has 2 zeros. When you have 5 of them, your life is easy. You go with the 3 zeros. Whatever column or whatever row has 3 zeros, that should be your leading cofactor expansion. So in that column, we have only one that is non-zero. So we take 1 times the determinant of 3 by 3 matrix. Now, if you observe the 3 by 3 matrix, we are lucky because we have 2 zeros in this 3 by 3 matrix. That means we can use the inspection again on 3 by 3. In this 3 by 3, we have 2 zeros in the first column and 1 non-zero entry. So we take our non-zero entry and we multiply the determinant of the rest 2 by 2 matrix. So 1 times determinant of the 3 by 3 matrix. But in this 3 by 3 matrix, we can use another inspection. So that 2 times the determinant of the 2 by 2 matrix. And we know how to find the determinant of 2 by 2. It's the right diagonal minus the left diagonal. So this is what we did here. 1 from 4 by 4, 2 from 3 by 3, and this is the determinant of 2 by 2. But when you use this, you have to remember about your sign, the position. This was plus for 4 by 4, so our 1 is plus. And this 2 is plus for our 3 by 3, so this is a plus 2. And you multiply all of them. You don't add them. Okay. Now, who did the right one correctly? Let me take the attendance before I forget. Today is 27 right here. Harp, Jose, Mehrab, Kenyan, Bora absent, Andy, Chuyan, Jackson, Christian, Emmanuel, Gregory was here, Abid absent,
What's the answer for the left one?
14. You didn't get it? Vlad absent, Ethan here, Elsa here. Huh?
Your answer's wrong.
No. The answer is 14. Why is my pants? Okay. The right one. Any volunteer for the right one? Elsa, will it right?
I don't think I found all solutions, but you told us that if there are 2 identical rows, that would automatically make determinant 0, right?
Mhm.
So if we can get C plus 1 equal to -2 somehow, then it would make the row 1, row 2 identical. So I put C plus 1 equals -2, and I found that one of the solutions is C equals to -3.
Mm-hmm.
And the other options, other choices, I don't know.
And this is correct. One of them is -3, I think.
The other one of the properties is if a row or column is all arrows, the determinant is also 0. So the first column, if you get C minus 1 equals 0.
C minus 1, 0. That gives you C equals 1. Yep, this you are correct. I think they're correct. Yeah. Cool. So you guys use inspection, like you inspected what makes it 0 or what makes it identical. But if you don't want to use inspection that way, you can use inspection the normal way. This column has 2 zeros, so we can expand about this number. That means we're not going to use this, we're not going to use that. So it's opposition, plus, minus, plus, minus, plus. So 1, so determinant is 1 times. The determinant is 2 by 2. Now C, so C minus 1 times C plus 1. That's the determinant of the right. And we are subtracting the determinant of the left. Not determinant, sorry, the product. Minus negative 2 times C minus 1. In other words, if you multiply this, these are conjugates, so you get C squared minus 1. Minus and minus turn into plus. 2C minus 1, so C minus 1 plus 2C minus 2. We distribute, which is this C squared, sorry, my bad. C squared plus 2C minus 3. So this is the determinant of this matrix. And to be singular, the determinant is 0. So we want to see if this is 0, then what's the value of C that makes this 0? So we have a quadratic equation. How do you solve quadratic equation? Start with F. You don't need any formula. Factoring.
There's already
2 numbers multiplied to negative 3. Combined to positive 2.
3 and negative.
Positive 3, negative 1. So C plus 3, 0 gives us C is negative 3, which was given by Elsa. C minus 1, 0 is equals to 1, which was given by Mehra. Okay. Yeah, 2 F's. One is formal and one is logic. To be honest, I wasn't thinking about logic. I was always thinking about the formal method. Every day we all learn something new. Thank you guys for showing me the new method. Any question? With this, we are done with chapter 2. Ta-da! So you have your homework. And one question less because this is B. We just did B.
You're releasing the homework today.
You have 1 week to do.
Wow.
This due date will be next week, Monday midnight.
Yeah.
But tonight midnight, you have 1.5 homework.
Yeah. Yep.
1.5 tonight.
Yeah.
Chapter 2 next Monday midnight. Any question? Okay. So we are studying chapter 3. Chapter 3, the topic is vector space. Okay? Vector space. Now you may wonder, what is vector space? Well, vector space is full of vectors. What is vector? Vector is a matrix, a column matrix. Okay? A column matrix is called vector.
1 by n.
N by 1. Depending on which vector space you are on, you have that many rows. So if you are in R2, then you have 2 rows in a matrix. If you are in R3, then you have 3 rows in a matrix. So the difference between vector and points is that vector is written in a matrix form and point is written in XY form. Now, instead of going through the entire section, I want you to watch a cool video so you can enjoy learning with visuals. Okay? Oh, I forgot to again share my sound. So let me share again. Share with sound. So enjoy.
The fundamental, root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, Broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes, and in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have two vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these two vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not...
What does that mean? It means every vector, the original vector has to start from the origin, okay? So if you're making any vector anywhere, one end has to be at the origin, the other end has to be where the points are, or the specific point is. Except for this case, when we add or subtract two vectors, then one vector starts from the origin, and then the other vector starts from the tip of the original one, okay? This is what they meant.
some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those two vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, negative 1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus negative 1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like negative 1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or negative 1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding. So there are your vector basics, and in the next video, I'll start getting into some pretty neat concepts surrounding vectors, like span, bases, and linear dependence. See you then.
So in our next class, we are going to do some operations with these two operations. I mean, some questions we do with these two operations, matrix multiplication addition and scalar multiplication. Is that it?
When you're like making images, when you're making images bigger and you're like scaling the images,
Scaling. So you multiply your vector with a number by a number.
okay, so that's just linear algebra. Okay,
Mhm.
have a good day.
You too.
I need to catch up with these topics. My other classes have been crazy. I've been getting beat up lately. But I'm gonna catch up by November 17th.
Do the homework. Don't forget to do the homework.
I will. I already handed it in.
Good job.
And
Mhm.
oh yeah, but you might not be happy because like towards the end, I only put the ends down, so I might not get credit for those questions.
Exactly.
Yeah.
Don't do that.